We're going to look at a few more trig questions and go through a few of the slightly different looking questions from the mixed exercise in chapter 7. We're going to look at questions 11, 13 and 14. So just to skim down and have a brief glance at each of these before we dive in. The first one involves cos of x minus 60. What's a bit strange about it is that instead of asking you to solve this equation directly, they initially ask you to show that tan x is equal to something. In other words, somehow it should be possible to convert this equation into a different equation. And the idea behind this is that having written it as tan x equals a number, you should be able to solve it. That's why the second part has a hence. Now, hopefully we can see that the most obvious way into this question is involving the cos x minus 60. We've got a rule for multiple angles, cos of a plus b, cos of a minus b, so we can work with those. Question 13, it gives you some information here that might come in handy. Alpha is acute and tan alpha is 3/4. It's tempting to jump straight to the calculator and find the value of alpha. We know it's acute, we know that tan alpha is 3/4, so we could just find alpha straight away. And that's one approach. I'm going to show you a few different approaches that might work more generally if you had less information or more obscure information. But again, it involves multiple angles, theta plus alpha, but it's got a cos and a sine, so there's a bit more work to be done. The next part of the question gives us some specific information about sine and cos and asks you to evaluate certain things. So this will involve potentially using the previous part of the question and potentially using the multiple angles in a similar way, but not directly related to the previous part. In question 14, it starts with a proof. It's a counterexample proof. With counterexamples, a good thing to bear in mind here is that potentially you can find a really easy counterexample. So start off with something simple. Think of some nice easy numbers that you can quickly and simply put in to demonstrate that the left-hand side and right-hand side don't always match. Since this claim is that sec a plus b is equivalent to sec a plus sec b for all a and b, if you can find any value of a and any value of b that makes it false, then you're done. I would steer clear of undefined results. I suppose you could prove that if sec a plus sec b gives a sensible finite answer, but sec of a plus b is undefined, then that kind of breaks the statement as well. But if they were both undefined, it wouldn't be clear whether or not they were undefined in the same way, perhaps. So if you can, find some results where sec a plus b gives a sensible value, and sec a plus sec b also gives a sensible value, but they're not the same value. If you want a bit of a bonus problem to solve with that one, see if you can come up with an elegant formula for sec of a plus b. We've got sine, cos and tan multiple angle formulae, but you might want to have a go at creating a sec, cosec or cot multiple angle formula. It shouldn't be that horrendous, and you might find that you can generate results for instance, sec a plus b in terms of sec, cosec and so on. And I can certainly imagine it should be plausible to get a result involving cot for cot of a plus b, but I'll leave that to you to try out. And for the last part, there is a nice trigonometric proof. We have to demonstrate that tan theta plus cot theta is equal to 2 lots of cosec 2 theta. The cosec 2 theta is quite nice because although we don't have or haven't necessarily worked with double angle formulae for sec, cosec and cot, we know what sec, cosec and cot are in terms of sine, cos and tan. So we've got some stuff we can do there. Our first question, given that 2 sine x equals cos of x minus 60 degrees, show that tan x equals 1 over 4 minus root 3. Well, I would suggest for something like this, we start with whichever bit of the equation can be most easily broken down, manipulated, converted into something different. So we'll take the cos of x minus 60 and we'll apply the cos a minus b formula, which if you recall is cos a cos b plus sine a sine b. We have the opposite signs inside as we do outside for the cos a plus minus b formulae. From there, we can use our standard results. You'll remember that cos 60 is a half and sine 60 is root 3 over 2. So that simplifies things down for us quite a bit. Now at this point you want to start thinking, what am I trying to get to? What am I intending to show? And since they want to show that tan x equals something, it makes sense to try to group the sine terms together and group the cos terms together and try some division. You could instead at this point divide through the entire equation by cos x. That would eliminate the cos x and it would turn both of the sine x terms into tan x. But I've decided to group the sine terms first. I've doubled everything to start with, so I don't need to worry about the fractions. And then I collect the sine x terms on the left-hand side. I can already see that the 4 minus root 3 term that I was expecting has appeared. So all I need to do now is divide by cos and divide by 4 minus root 3. And there's my answer. For part B, probably the main purpose of picking this question is to highlight the fact that this is a hence solve question. Some people will go right back to the drawing board with some of these. This one's possibly more obvious than others, but whenever you're trying to solve something tricky in part B, you should always ask yourself whether there was a purpose to part A that will help you with part B. So the first thing I would say here is, if I'm trying to solve this equation, that's equivalent to solving the equation that I demonstrated it was equivalent to in the first part of the question. So now we're solving tan x equals a number, and we do that in the usual way. We just substitute into the calculator to get the inverse tan or arctan of 1 over 4 minus root 3, and that gives us a principal value. That value itself is within the range, because the range we've been given is everything from 0 to 360 inclusive. So we get an entire period, or in this case, because it's tan, it's 2 periods of the graph, we'll get a full 0 to 360 span, and we've got the first solution, 23.8. Because it's tan, I'm not even going to bother drawing the graph. I know that there's no complicated mirror symmetry to worry about, like with sine and cos. All we have to focus on is the period of the graph. It repeats every 180 degrees. So if we add 180, we'll get the next solution. And we can hopefully already see if we add 180 again, we'll get a value that's bigger than 360, so there's no point trying anymore. We've got our 2 solutions. I would recommend you check these in the original equation that you were solving. So try 2 lots of sine 23.8 and see if it's the same as cos of 23.8 minus 60. That's a reasonably quick thing to practice and to check that you can do, and it will reassure you that you've done the correct thing, you've not made any silly mistakes along the way. The fact that it's a show that in part A will help you with that, so you're probably feeling reasonably confident about your answers. The next question, question 13. There's a few different ways to look at this, and it's tempting at the beginning to say, well, if tan alpha is 3/4, then I'm going to go to the calculator and find an approximate value for alpha. We can just do inverse tan of 3/4. The problem with that is it gives you some messy decimal, which if you're trying to prove something, you've got to be very careful using messy decimals. Just because the calculator gives you an approximate value for inverse tan of 3/4, and it can therefore give you a value for sine of the approximate value of inverse tan of 3/4, and the calculator thinks that's 3/5. That doesn't prove that it is 3/5. It just proves that the decimal expansion is very close to 0.6. If you want to prove it, there's a few ways to do it. What I'm going to show you first is my original attempt at the question, and then what I'll show you after that is a couple of more efficient methods that I used after working through and realizing that I wasn't working as quickly and efficiently as I could be. Generally, this is how it works when you're tackling a maths question. You try something, and if it works, that's great. But when you've finished, you'll probably look back and realize there are shortcuts and efficiencies that you could take the next time round. But I want to model for you what it would look like if you just dive in and do sensible things. And the most sensible thing here will be to deal with the fact that you've got sine of theta plus alpha, and you've got cos of theta plus alpha. So we're going to work at breaking those apart. But before I do that, I'm also going to consider the tan alpha equals 3/4. I'm going to start jotting stuff down on the right hand side of the page that I might use later. The fact that tan alpha is 3/4 gives me a connection between sine alpha and cos alpha. That's reasonably obvious because I'm thinking, well, I've got sines and coses in my identity. The information I've been given is in terms of tan. I'm going to need to turn that into something involving sine and cos. But so far, having the fact that sine alpha is equal to 3/4 of cos alpha, that's enough. I could do more with it, but I'm not going to yet. I'm going to leave it like that and see if that's sufficient or whether it comes in handy for me. Next thing I'm going to look at is the left-hand side of the identity. The right-hand side is about as simple as you can write it, so unless you have some crazy flair of genius, I wouldn't recommend starting with the right-hand side. The left-hand side can be broken apart using the trig addition formulae. So sine of A plus B gives sine A cos B plus cos A sine B. Cos becomes cos minus sine sine. So we should get something like this. There's a lot of letters involved in there. Theta crops up 4 times, alpha crops up 4 times, sine and cos each crop up 4 times, and all in slightly different places. So try to keep your head and look carefully at what you've got. And don't get too bewildered by the fact that you've got such a long line of algebra. Think about what you're trying to get to. The aim is to end up with everything cancelling out apart from 5 cos theta, which means anything involving alpha should disappear. And I'm probably going to find this expression useful because even though I've got sine alpha appearing and cos alpha appearing in multiple different places in my expression, I know that I can eliminate at least one of them and convert it into something involving the other one. At some point I'm going to need to eliminate the other one as well, but we'll worry about that when we get to it. So the first thing I've done here is pulled out sine theta as a common factor and pulled out cos theta as a common factor. What I'm expecting is that the sine theta part will disappear and the cos theta part will become 5 lots of cos theta, just based on what I can see on the right hand side. But now it's time to bring in the sine alpha equals 3/4 of cos alpha term. If I do that, I find that the original bracket here turns into 0, because 4 lots of sine alpha will be 3 lots of cos alpha, so they match and they cancel out. On the right, things are not quite so straightforward. 3 sine alpha becomes 9/4 of cos alpha. So I've turned it into something that only involves cos alpha, but that's not quite sufficient. It would be nice if we could get rid of that entirely. I know what I want it to be. I need 25/4 of cos alpha to be equal to 5 because it needs to match the right hand side. But how do I prove that? Well, that comes back to this term on the right. So throughout this proof, in order to not clutter things up, I've kept the proof as one consistent line, left hand side equals, etc. But on the right, I'm working with anything else that comes up that might be useful. And if it doesn't go anywhere, it's not such a problem because it's not got in the way of my overall flow. But let's now work with sine alpha equals 3/4 of cos alpha. Let's square both sides. Why would I do this? Well, I'm trying to find the value of cos alpha, and the connection between cos and sine comes about through the sine squared at cos squared equals 1 identity. So now I've got this, I can replace sine squared with 1 minus cos squared. And that means I can rewrite cos squared alpha as 16/25. This is where hopefully you recognize there is a part of the question we've not yet used. Alpha is acute. That should be relevant. It should be something we need, otherwise they wouldn't have told us the information in the first place. If alpha is acute, that gives us some useful information. We can't tell alpha is acute just by looking at tan alpha. You could say, well, tan alpha is positive. That happens for acute angles. That's true, but it also happens for angles that are between 180 and 270. So it hasn't really narrowed it down for us. But if alpha is acute, then cos alpha and sine alpha are both acute as well. I mean, cos alpha and sine alpha will both be positive because alpha is acute. And that means when we get to cos squared equals 16/25, and you're saying, well, that means cos alpha is either plus or minus 4/5, we know cos alpha is positive 4/5 because alpha is acute. As soon as we got that, we can sub it in over here on the left. Cos alpha becomes positive 4/5, and therefore we get the 5 cos theta that we needed. Now let's look at a couple of alternatives for doing part A before we move on to part B. Here's my second alternative. If tan alpha is 3/4, we can use essentially the method that we had before, the fact that sine squared at cos squared equals 1, but I can do it a bit more efficiently. I can say that tan squared is 9/16, and I know that sec squared is 1 plus tan squared, so I can replace that. I can find sec squared, I can find sec, and therefore cos. So similar reasoning, but a little more efficient. Once I've got cos, I can do sine squared is 1 minus cos squared, and again using the fact that alpha is acute, I get sine alpha as 3/5. Now if I've got both of those, then I can substitute them directly into the formula, as we'll see in a second. Here's an even nicer alternative. we know that alpha is acute, so we can consider the right angle triangle that you would get if you had angle alpha in your right angle triangle. And of course the adjacent and opposite sides need to be in the ratio given by tan alpha equals 3/4. So this is our triangle. Alpha is the angle that gives a ratio of 3/4 between the opposite and the adjacent sides, but a bit of Pythagoras will show us that the hypotenuse needs to be 5. And once you've got that, we can directly read off sine alpha and cos alpha. It's a very useful idea, and in fact you can extend it a bit if you're thinking about unit circles, and then you can take into account negatives for one or both of the legs of the triangle as well. The next bit is the final part of part A, just showing you what it looks like if you've originally found the values of both sine alpha and cos alpha. You'd still expand things the same way, but the next step is just to substitute in the values for cos alpha and for sine alpha. So cos alpha gets replaced with 4/5 wherever it appears, and sine alpha similarly. Once we've done that, simplify things down, you'll find that everything disappears apart from 5 cos theta, which is exactly what we wanted. And now for part B. It's not too complicated, part B. Just put it straight up on the screen. You've got cos of x plus 270. We break apart in the usual manner, and things cancel, and we end up with a 0.6. I'm using the fact that I know cos 270 is 0, and I know that sine 270 is -1. A quick way to identify that is to visualize the unit circle. Try moving 3/4 of a turn anti-clockwise from the positive x direction, and that'll tell you what, that'll give you the 270 degree mark. It has 0 in the x direction and -1 in the y direction, so cos 270 is 0, sine 270 is -1. Of course, you've got calculators for this kind of thing as well. For cos of x plus 540, the method is the same, but different things cancel out. And it turns out we still get things that involve 0.6 and 0.8, so I thought it might be useful to look at the unit circle to make sense of that. They've told us the value of sine x and the value of cos x. These are not independent things, they're referring to the same angle behind the scenes, x. So the angle x must be an angle that corresponds to a sine of 0.6 and a cos of -0.8. In other words, the y-coordinate on the unit circle is 0.6 and the x-coordinate is -0.8. And that is the point that I've marked here. That point on the circle has the correct sine and the correct cosine. They are the x and y coordinates of it. Cos and sine are the x and y coordinates. But then we can think about cos of x plus 270 as being, what's the x coordinate if we move this point around another 270 degrees? So continue to turn another 270 degrees and see where you get to. That's the idea. So if we take this point and we turn it another 270, 90, 180, 270, it ends up pointing somewhere like this. And it kind of makes sense. If you look, my arrow is a bit off, but a value of 0.6, a positive 0.6 makes sense. In fact, being 0.6 rather than 0.8 is also sensible because the x and y coordinates kind of get switched. If you do a 90-degree rotation, you'll see that instead of having a shallow negative gradient, it now has a steep positive gradient, the vector that I've drawn from the origin to the point. For the second one, we're adding 540, which is going quite a long way round, but if you recall, 540 is equivalent to 360 plus 180. So after you've gone whizzing around a little way, you'll realize that you're just pointing the exact opposite direction to the way you were before. Now, not only can we see what the cos of x plus 270 and cos of x plus 540 are, but from these we can also infer sine of each one. So with the blue one, for cos of x plus 270, we would have a cos value of 0.6 and a sine value of positive 0.8. Whereas for the purple one, cos of x plus 540, we're getting a cos value of 0.8, which is what we expected, but we get a sine value of minus 0.6. And so the unit circle can be a really helpful way to get a read on some of these things and to put them in a more logical context so that you can verify independently that your results make sense. This last question we're going to look at is trig proof. And what I'd suggest for the first part, they're looking for a counterexample. We need to show why this thing is not necessarily always true. The statement is a strong statement. It's a statement that those two sides, the left and right hand sides, are equal for all values of a and b. To demonstrate that that statement is false, it's necessary only to find an example of a value of a and a value of b for which the left hand side and right hand side do not match. Now I'd recommend that you pick values that you can state directly and exactly the values for sec a, sec b and sec a plus b. If you're relying on decimal approximations, that's not going to constitute a very thorough proof. But also you need to be careful to avoid values that give asymptotes for sec. So any values that you could put in for the angle that would make cosine of the angle 0 are going to be undefined when you do sec of the angle. So I've decided to go with 30 degrees and 60 degrees for A, in fact 30 degrees for A and for B, giving 60 degrees for A and B. That means that we get nice exact values. We get a half from root 3 over 2 when we do cos of pi by 6 and cos of pi by 3. And therefore we can easily calculate an exact value for the left hand side and the right hand side and show that they don't match. So that's what I've tried here. We put pi by 6 in here as both a and b. There's no rule that says you have to have different values for a and b, because the statement doesn't say that this is true for all distinct values a and b, or all values a not equal to b. It just says for all values a and b. So if we can find any pair of values that don't match, we've disproved the original statement. Since cos of pi by 3 is a half, the reciprocal is 2, but because cos of pi by 6 is root 3 over 2, the reciprocal, 2 over root 3, added to 2 over root 3 again, gives 4 over root 3. They're not the same, therefore we're done. That's a counterexample. For the next part of the question, this is a proof, and it's a classic example of a proof where there's not necessarily an obvious direction. You can't look at it and say there's something complicated on the left and something simple on the right, so I'm going to move from left to right. And you can't easily do it the other way either. It's more like the left and right hand sides are both potentially complicated, or something that you could work with and change into a different format. So we can convert the left hand side and the right hand side both into some more primitive form. Generally speaking, something involving sines and coses, so it's easier to compare. I'm going to start with the right hand side because I can immediately see some things that we can do with that, and then we'll look at the left hand side after that when we see how far we get with the right. Because we don't have a formula directly for cosec 2 theta, we're going to use the fact that cosec is 1 over sine, so we have 2 over sine 2 theta, and we can construct pretty easily the expansion for sine 2 theta. This uses the fact that sine a plus b is sine a cos b plus cos a sine b, and if a and b are the same, we get 2 lots of sine theta cos theta. We can simplify slightly, but at that point there's not a lot of value in trying to mess about with that too hard to turn it into tan theta plus cot theta. It's going to be much more worth your while moving across to the left hand side and doing a bit of work with those, turning tan into sine over cos and turning cot into cos over sine. Then we've got 2 separate fractions, whereas the right hand side currently we're looking at one single fraction. So the logical thing will be to combine our 2 fractions that we've got over on the left hand side, which confusingly I've written on the right hand side, but it makes no odds. We're going to combine those fractions into a single fraction. Hopefully at this point you recognize the numerator. Even if you didn't remember that sine squared or cos squared was equal to 1, the fact that we're trying to demonstrate that these two things are the same means that you should be thinking to yourself, what is it that's different? Because those different bits should disappear. And that's exactly what happens. Sine squared or cos squared is 1, therefore the left hand side simplifies down to 1 over sine theta cos theta in exactly the same way that the right hand side does. Once we've got that, we're not quite finished, but we're nearly finished. Notice that the left hand side and the right hand side both are equivalent to the same thing, so I just label that thing P. And then we make a brief statement. Since the left hand side and the right hand side are both equal to P, Therefore, we know the left-hand side is equivalent to the right-hand side. And we're done.